Déborah is going to present.
Thank you very much. So thank you very much also for inviting me and giving me the opportunity to present my work. This workshop is really great. I also followed a previous workshop online, and I find it's really great to have all these talks online that we can have access to. So today I'm going to present a work on how we do uncertainty quantification in Gaussian graphical models in the context of high-dimensional data. This is joint work with my former postdoc advisor, David Russell at Prof University, and Jack Jewson, who is now at Monash University. So I'm going to present first the problem of graphical modeling and how we can do sparse inference in the context of high-dimensional graphs. Then I will present a strategy for doing posterior sampling, actually a couple of them, and then present some numerical results on algorithmic efficiency that we obtain, and also some theoretical guarantee. So first, quickly, I will recall the problem of graphical modeling. So it's a very broad problem that you can apply when you are interested in finding the partial dependency structure within some observed variable. Okay, so in a very general form, you can say that you observe p variables, or a random vector of size p, and you are interested in estimating the partial or conditional dependency between pairs of variables conditionally on the other. So we are interested in these laws of these pairs, conditional laws. Okay, and the graphical model is simply a visual way of representing the partial dependencies that you have inferred. So imagine if you infer 3 variables, well, you could represent their partial dependency structure by putting each variable as a node. So here you have, for example, hours spent on TV, education, and wage in some population, and you can represent which variables are partially dependent on each other just by drawing an edge in this graph. So of course, this is a very challenging problem when you observe many variables, so when the number p is large, and this happens often in applications. This makes the problem of finding the partial dependency structure very challenging, because the number of possible models that, you're searching into a very large space of possible graphical models, and in particular when you use these models in a genomic application where you are trying to infer which gene expressions are partially correlated with each other, you may be searching among a large set of genes of interest of order hundreds or more. This also happens when these models are used in neuroimaging, where each observed variable is a level of activation of some region of interest. And also in this case, you may want to include many regions of interest in your analysis. Okay, so we were interested in designing an inference method for a graphical model that is scalable to the high-dimensional setting. And also in this case, recovering a sparse graphical model is more interpretable. So this is what we will be looking for. But also because we are looking into a very large space of models, and if you have a relatively small sample size, you may end up with having several models that would well explain the dependency structure in your data. So you need also a method that can account for the uncertainty that you have in inferring the dependency structure. Okay, so one way to simplify this challenging problem is to assume that the observed variables are Gaussian. Okay, and for simplicity, you can assume that they have a mean 0. That doesn't matter much. And they have an unknown covariance matrix sigma. So that simplifies the problem of finding the dependency structure, because if you look at the inverse covariance matrix, which is also called the precision, then this inverse precision matrix fully encodes the graphical model within your observed variables. And this is a well-known property of the Gaussian distribution, that, well, if you look at the precision, at the entries of the precision matrix, if you look at an entry omega ij, and if this entry is equal to 0, that means that the two variables yr and yj are partially independent. Okay, so that means that if we can estimate omega, then we can infer the graphical model that encodes the partial dependency in the observed variables. And I will call Z the graphical model. So it's a set of binary variables that will indicate for each entry of omega, or the upper triangular, which ones are 0 or not. Okay, so our goal will be to estimate the precision matrix, infer the graphical model Z from some observation of our variables, what we call Y or data matrix, which is simply an N by P matrix. Okay, so as I said before, if P is large and we are looking in a graphical model in a space which is super exponential in P, then we are interested in recovering a sparse model that will be more interpretable. And the first idea that may come to your mind, or that you already know, is that you can do simply a penalized maximum likelihood estimation. This is a well-known method that we call the graphical lasso. I mean, it doesn't need to be a lasso penalty, it can be different types of penalty, but this is maybe the most well-known method that was independently proposed by 2 sets of authors. There are many variants also to it, but the idea is just to find the estimates within the space of precision matrix, so you need to search among matrices that are symmetric and positive definite, that would maximize a penalized criterion, where the log likelihood would simply be the Gaussian likelihood, okay, and the penalization can be in terms of, well, L1 norm of the matrix in the G-lasso, but it can also be L2 norm, and it would be a rich type estimate. A second idea that was proposed, actually just before the G-lasso, is to do a node-wise regression in a also penalized manner, basically to do a lasso p times. So the idea is that, well, if you have Gaussian variable, you can also look at the conditional distribution of one variable given the other, and this is still a Gaussian distribution, and the mean is expressed as a linear combination of the other variables. And the coefficients that are in this linear combination can be expressed as the coefficients in the precision matrix. So that means if you want to obtain an estimate of one column of the precision matrix, you can try to regress one variables onto the others. And that's the idea of penalized node-wide regression, is that you find the regression coefficients that by regressing a column of your data matrix onto the other, and you do that with also L1 penalization on the regression coefficients. So that would give you an estimate of one column of omega. Okay, if you do that p times, you can recover an estimate of omega, of the full matrix. Of course, there are some disadvantages to use this penalized MLE methods, or this penalized node-wide regression. It's well known that they don't control well the false discovery rate. Okay, so they tend to recover a lot of. They have a lot of false positives, and also in the case of penalized node-wide regression, as you estimate each column independently, you are not guaranteed to recover an estimate of the precision matrix which is positive, definite, and symmetric. Okay, so that can have also some interpretation problem. And of course, none of these methods provide uncertainty quantification. Okay, so to provide uncertainty quantification, a useful paradigm is Bayesian inference, and what we propose is to do this with Spack and Slab prior, so which means choosing a particular prior that will help us to infer the property we want. So in particular, sparsity. Sparsity. So the idea of the Spack and Slab prior for a Gaussian graphical model is to write the prior distribution on the full matrix as a almost factorizable product of univariate distribution on each coefficient. So you need to distinguish between the diagonal coefficients and the off-diagonal, simply because the diagonal coefficients need to be positive. So for the diagonal coefficient, we choose an exponential distribution, but for the off-diagonal coefficients, this is where we will put a Spack and Slab prior. Of course, I said it's almost factorizable because, well, you need to add your positive definite constraint. So this is why we have an extra indicator. So the Spack and Slab is the prior that will enforce our sparsity property. So the idea is, well, to construct this prior on the off-diagonal coefficient as a mixture of a Dirac measure at 0 and a normal distribution with a certain variance. So it has a nice interpretation that, well, a priori, each of diagonal coefficients of omega will be either 0, okay, if it's generated from the spike, or it's non-zero when it's generated by the slab. Okay, so and there is a weight theta, a hyperparameter that weights this this mixture. Okay, so the higher theta, the less sparse is this prior. Of course, this is not the first Bayesian method that is proposed for Gaussian graphical models. The first one was based on G-Wishart prior, which is the conjugate prior for the multivariate normal distribution. I didn't put a reference for the first work. I put reference on, well, groups that have worked on how to scale up the computation of the Poisson distribution induced by this prior, which is one of the main drawbacks of using the G-Wishart prior. It also has some interpretability issues because the hyperparameters are not interpretable. Another set of works use shrinkage priors, which, well, try to infer the property of sparsity by, well, shrinking the coefficients, but not strictly putting a prior on sparse matrices. So they have computational issues. They cannot scale up to large settings, and also they have consistency issues. A recent line of work, which is actually very efficient, are approximate or quasi-Bayesian methods. There are two works that are in this line of ideas. So recent work for the G-Wishart prior and one with the spike and slab. So in this case, the method doesn't target the exact posterior, but an approximation that can be good enough in some application. And these methods scale up to thousands of variables. So our contribution is to propose a scalable algorithm for computing posterior distribution implied by spike and slab prior. So as I will see, we are orders of magnitude faster than existing fully Bayesian methods, and we also favorably compare to quasi-Bayesian methods. And we also have some theory on it. Okay, so now I will talk about how we compute the posterior distribution for the spike and slab prior. So it's not an easy task a priori because, well, our posterior is a bit complex, so it's proportional to our Gaussian likelihood and to our GGM spike and slab. Okay, so I have, well, these factors are the ones as, I showed before. We also have this indicator that omega needs to be positive definite. And here I also add a restriction that the maximum degree a priori is bounded by some large number that I call d bar. Okay, so the one way to try to solve the problem of computing this distribution is first to apply a reparametrization trick. So it's not the same reparametrization trick as in variational inference, but I called it like this because it's really a trick, and it's a reparametrization as well. So the idea is, well, we cannot directly express in a closed form this posterior, but we can try to look at the posterior conditionals. Posterior conditional means I look at the posterior conditional of one column given the rest of the matrix. So imagine I focus on the last column. I call that omega dot p. And I will introduce new variables that fully characterize that column. So I will introduce an inclusion vector z. Okay, that is just an indicator vector of which variables are non-null, which of diagonal in that column are non-null. I will call u the minus the non-null coefficients in omega p. And I will call v omega pp minus this quadratic form involving u and the rest of the matrix. I mean a block of the rest of the matrix. Okay, so the one thing to remember here is that, well, with these three variables, z, u, and v, z being the indicator vector, I fully parameterize one column of my matrix. Okay, so why is it useful? Well, because now I can actually cut half of the interactability of the posterior conditional. So what we can first show is that, well, the posterior on the reparameterized variables, so u, v, and z, conditionally on the rest of the matrix, is a product of a normal distribution, a gamma distribution, and then a distribution on the indicator vector z. And the advantage here is that the normal distribution has the dimension of the non-null entries in z. Okay, so if z is sparse, I only need to sample from a low-dimensional normal distribution. The gamma distribution on the reparameterized variable v guarantees that we will sample a matrix that is positive definite. And then, well, I said we solved half of the intractability problem because we still have a distribution on the indicator vector, which is intractable, although we have the exact expression, but the normalization constant is unavailable when p is large, okay? Because you would have to compute it for everything. Okay, so we still have this intractability problem for sampling the indicator vector, but for sampling the variables conditionally on the indicator vector, now we know how to do it. So how we can first sample everything? So as I said, we can sample for the posterior conditional. So what is very intuitive is that, well, we can construct a block deep sampler that we sample each columns of omega and iterate over the columns. Okay? So that's the idea. Now I've introduced subscript to specify that, well, we will do that for every column of omega. But as I said, we have this intractability of how we sample the indicator vector. And to do that, we can, since we have the analytic expression of this distribution, we can we can use a Gibbs or Metropolis-Hastings algorithm. You can also put Gibbs as a Metropolis-Hastings algorithm where the proposal is the exact conditional. So I will just explain how we can do Metropolis-Hastings to sample or approximately sample from this distribution. So the idea of Metropolis-Hastings is to have a suitable proposal distribution, which I will call Q, that you can sample from, and you will accept or reject this new sample with a probability given by the acceptance ratio. Okay, and by doing that, and doing multiple Metropolis-Hastings steps, we can obtain approximate sample from this intractable distribution Zj. Now, we are in a setting where we know how to do these things. It's a very common problem in Bayesian model selection. Even in linear regression, there are many possible algorithms to, or possible proposal distribution for this. You can use just Gibbs, a nested Gibbs here, birthday swap, which is just proposing to kill or to give birth to a new edge. Okay, or you can use also the locally informed thresholded proposal, which is just a weighted version of the birthday sampler. So all these proposals are local because, well, they only propose to do one change in the indicator vector z at a time. So to modify p entries of z, you would need to do p steps of p Metropolis-Hastings steps. Okay, one other idea that we had is to try to accelerate the sampling from this from the intractable distribution on the indicator by using a global proposal. And to do that, I will put again the expression of this intractable distribution that we're trying to approximate from. Well, it looks like a binomial distribution, but there are these extra terms that are a bit annoying. Well, the other thing is that this distribution has a lot of similarity with the distribution that you would have in linear regression if you were to put a spike and slab prior on the regression coefficients. And this is the same idea as I presented before in the penalized node-wide regression problem, is that, as I said, the conditional distribution of one variable given the other can be expressed as a normal distribution where the mean is a linear combination of those other variables. So if I were to treat this problem as an independent problem of regressing one variable onto the others and putting a standard Bayesian model selection method, which would be here the spike and slab, and if I were to write the posterior distribution on the indicator vector of those regression coefficients, I would obtain an intractable distribution that would look like my target. Okay, and so this is useful because, well, first, it has been proved by this, by Eva Chade, that this linear regression posterior is actually consistent for estimating one column of the graphical model. Okay, so that means, well, this is potentially helpful for designing a proposal. Okay, so that was our main idea. Well, if we use this linear regression posterior, but an exponentiated version of it, or a tempered version of it, this is to avoid over concentration, then we have something that is very useful because, well, it's independent, first, of the state of the Markov chain, because it's independent of the rest of the matrix in omega and the previous state of Z. And also, I can modify all of the entries of this indicator vector at once. Moreover, because it's an independent proposal, then I can sample from it as a pre-processing step, even before starting my block Gibbs sampler, and I can do also that in parallel for each column. So there is a lot of parallelization that can be done. Do I have 1 minute?
Yeah, yes.
Okay. So I guess I'm going to present just a few empirical results, and I will leave the theory for today. So we have implemented our method in R. I mean, actually, everything is implemented in C, but it's an R package. And we compare to what exists, so other R packages that have also implementation in C, in particular implementing shrinkage prior and J-Wishart prior. We have multiple simulated settings where omega has a different structure. We test low to high dimensional settings, so P up to 1,000, and relatively small sample size, so N is less than 5p. To compare computational efficiency, we compare the estimates that are obtained by running this algorithm for two Markov chains initialized at different places, and we look at the difference in estimate versus the runtime. Okay, and this is the type of plot we obtain. So here I plot this difference of estimate versus runtime. So the best is the lower left corner. And our methods are the colored one, and the black one are the fully Bayesian method, and the gray one are the quasi-Bayesian methods. So, and this is for p equal 100 for two different sample size. What we see is that, well, we scale in the same way as quasi-Bayesian method, and we are orders of magnitude faster than the fully Bayesian one. Okay, and for larger p, in this case, we cannot run fully Bayesian methods, doesn't scale, so we can only compare to quasi-Bayesian, and we also compare well. In terms of inference accuracy, since I'm running out of time, you have to believe me.
Can take
okay. Well,
let's continue because it's very interesting. Please take 2 minutes.
Okay, well,
whatever you.
Thank you. Thank you. Well, it's almost the end. I mean, we have a bunch of metrics to compare inference, not only computational efficiency, the mean squared error on the estimate of omega, and then different metrics linked to the estimate of the graphical model, so the power or true positive rate, false discovery, LUC, etc. And we also compare to frequentist estimate. But the main message here is that in terms of inference, all Bayesian methods compare almost the same, and we fall also in this category. Okay, well, I have an application to COVID-19 data, which is maybe I will skip in the interest of time. I had some theoretical results which I will also skip because I have a very important message at the end, because I want to recognize, to put the pictures of my collaborators, Jack and David, to advertise, well, our package, and also to advertise that next year in Lugano, in my university, we will host the European Meeting of Statisticians. So it's exactly 1 year from now. This will be a really great meeting. The scientific committee is preparing a very great program. We have a very beautiful lake around our campus is pretty new, and we are trying to make this a great event. So please come and well, ask me questions as well if you're interested. Thank you.
Thank you very much. So it's a great talk, and I think we have the opportunity to ask you for some details that you have skipped.
Sure,
So
sure. I would love to.
Are there any questions? Or maybe I can start. So, yes, can you talk about the theoretical guarantee?
Okay, sure, yes, thank you. Thank you for asking. That's what took most of the time, actually. So I mean, the idea is to characterize the computational efficiency of Markov chain is to characterize the mixing time, which gives you an indication of how many iterations you need to, to discard, or how many iterations are needed so that your Markov chain has converged to its invariant distribution. Okay, so the mixing time formally is the number of iterations at which your the distribution from your Markov chain is at a distance epsilon in the total variation sense from your target. And the way to characterize the mixing time is either via the conductance or the spectral gap. These are the classical methods, but in high-dimensional settings, authors have proposed to look at, well, the S conductance, which is a variation of the conductance concept that sort of focus on high probability sets. So with this notion of mixing quality, you try to ignore the sets that have very low target mass. This is useful to bound the mixing time because, well, you can use this S conductance to bound the total variation distance between, well, the distribution of your Markov chain after t iteration and the target pi. Why it is useful in the context of metropolis within Gibbs is because we can use, well, existing results, which we have a big tweak to our settings, which express how the S conductance of a metropolis within Gibbs algorithm relate to the S conductance of an ideal Gibbs sampler, which is intractable here. And it's expressed as, well, you have a lower bound on the S conductance in terms of the one of the Gibbs sampler, and the worst conditional spectral gap that you have in your metropolis Hastings step, plus a term that you hope to be small because it's, well, the mass on the complement of a set that on which you can characterize the spectral gap. So the main idea is that, well, if you can lower bound the worst in possible conditional spectral gap on a set of high probability mass, then you can quantify how close the S conductance of the metropolis within Gibbs is close to the Gibbs algorithm. And so to do that, well, we prove that when we use this global proposal, but we also have results in our paper on the local proposal, that the worst spectral gaps converge to 1, basically. So for any epsilon, and with probability going to 1, the worst case spectral gap will be greater than 1 minus epsilon. So that means that so in particular, it doesn't depend on the ambient dimension of the problem. So this is a dimension-free result. Okay, we have a bunch of assumptions, I guess. I can spare you that.
Thanks a lot. Other question? Can you say just a word about the COVID application?
Sure. Okay. Yeah. Thank you. I can go back to my slide on this. Well, it's a very preliminary study. It's just looking at, well, the log infection rates for a weekly in 300 counties or meta counties. We gathered counties that had very small population, and we look at the residual of this log infection rates after regressing these infection rates on known variables that are associated to COVID-19. Okay, so like the vaccination rate and also how strict were the COVID-19 policies in those counties. And well, we run our method on this residual log infection rate and extracted the edges of the graphical model such that the average a posteriori probabilities on those edges is greater than 0.95 to control the Bayesian FDR. And what is interesting about the graphical model we found is that, well, there are many edges between neighboring counties, which is intuitive because there may be some cross movements between populations, but we also have edges between faraway counties, which may indicate some correlation between the behavior of people in those counties.
Yeah. Traveling from big cities, maybe?
It could be actually movement, but it could be like a similarity in lifestyles or behaviors. Yeah. Mm.
It's very interesting, and especially I thank you for the very clear overview of this domain at the beginning.
Thank you.
To introduce the challenge. It's very rare to have the big picture of this sparse graphical Gaussian models.
Thank you.
Okay, so I think this is our last talk. It was wonderful to have you. I'm going to thank you again.